Welcome to Pre-Calculus. This is section 3.5, and we're going to be looking at some application problems today, dealing with the logarithmic model, the exponential growth model, and we're going to introduce a couple of new models to you. Let's first look at, so we're going to talk about 5 different types of mathematical models. Some of them we're familiar with. Let's look at the exponential growth model. So our exponential growth model is this y equals a e to the bx. It's very similar to the continuous interest of PERT. So a is the initial amount. My y is my ending amount. The b is your rate, the rate of increase. And then x is time. Time, a lot of times you'll see t for time, but x in this case represents our time. It's our control variable, and so that is going to be really where your variable will exist if you're going to ever graph your function. And b has to be greater than 0. Now, in order for that to work here, and your exponential growth, this has to be a positive exponent. That's all that's saying. And so here's what your growth looks like. It's this type of a curve. That's your exponential growth. Some places that we'll see this is population growth, or bacteria growth. So those are some applications for that. The next model that we're going to look at is the exponential decay model. And you can see it's very similar to the growth. The only difference is that your exponent here will be the opposite of b, or a negative exponent, which is going to cause a decrease over time. So your decrease over time would look like that. That's your exponential decay model. The values are the same, the a, the b, the y, and the x. And in this case, a good representation of that is radioactive decay. You'll use this in science, some chemistry. The next model that we're going to look at is called the Gaussian model, and the Gaussian model is a bell-shaped curve. It's used in statistics to represent a normal distribution. Normal distribution looks like this. You don't necessarily have to have your x and your y-axis in there. I'm going to go ahead and leave those out, but this is what your normal distribution would look like. And in a normal distribution, the mean occurs in the middle. So this is where your x, this is the mean of your data. We're also going to notice that the mean of the data will exist right here in your model. This is an x minus b. That's like a shift of your graph, and so that's going to represent the mean as well in the model. We don't have to be concerned with the other parts to this model other than just knowing what it will look like, and so that you can apply this type of an equation to it. We also have what's called a logistic growth model, and this model represents a rapid growth rate for a period of time, and then it's followed by a little bit slower growth rate. An example would be the spread of a virus. So, if you think about when a virus breaks out, it's going to increase pretty rapidly at first, and then it starts to taper off. This is what your graph would look like. This might be your x and your y-axis. Again, you don't have to be concerned about the a, the b, and what those rates or what each of those variables represent, but just knowing what the model looks like, and you'll be given a lot of the information in your problems with this model. The last model is the logistic model, or the logarithmic model. And the logarithmic model is one of 2 models, so you're using the natural log e or the log 10, either one of those. A good representation, or what you'll see using these models or the log, is when you do earthquake measures. How intense the earthquakes are, using the readings that they get for measuring how strong they are. All right, the log models look like this. Either one of them have a graph that is formed like that. All right, let's go ahead and look at some of these problems here and we'll solve them. Exponential growth and decay relationship here. An example, the population y in millions of a large city can be modeled by y equals 1.8 e to the 0.026 x. X represents 1990, or 0, 1990. In what year is the population of the city expected to reach 2.5 million? Well, here's what you do. There's a couple ways. You could graph these models on the calculator and find your solutions. We're going to go ahead and solve this one algebraically. So we go 2.5 million equals this model of 1.8. That must be the initial population at 1990. And this 0.026 is the growth rate. We would take 2.5 and divide it by 1.8. This equals e to the 0.026x. You're going to just continue to solve this. In fact, what you could do is divide, and you'd get 1.3889 equals e to the 0.026x. Now, in order to solve this, you're going to write this as a natural logarithm because of the base e. So natural log of 1.3889 equals 0.026x. You continue to solve that, and you would get x is equal to 12.63, which is approximately, it's in that 12th year. So if 1990 was times 0, going back to this, 1990 times 0, then we're looking at the year 2002. Okay, that's when it will reach 2.5 million. So this is an exponential growth. It's growing over time. Two hours after the bacteria was introduced into a culture, the population was 256. 5 hours after that, the population was 541. What will the population be 25 hours after the start of the experiment? Let's just represent this with an X and Y chart here. So if I've got 2 hours, the result is 256. If I've got 5 hours, after 5 hours after that, so that would actually be 7 hours from the start, it's 541. And then what we want to know is, what about for 20, I think you guys have 24 hours and I have 25, so 24 hours, what would it be? Well, in order for this to be able to solve this problem, you have to find the right model. It's going up, it's increasing, so this is exponential growth. Y equals a e to the bx. All right, my initial amount, we don't know times 0. So times 0 here, we don't know what it is. We don't even really have to find it. You could find it if you wanted to, but what we're going to do is we're going to use the time of 2 hours and then 5 hours later to be able to come up with our results. So at an initial time, let's say 2 hours, would be 256. The ending amount 5 hours later is 541 equals, or times e to the bx, and my time, how long did it take between these two readings, was 5 hours. We're going to solve this. So you take 541 and you divide it by 256, and this will equal e to the 5b. As I continue to solve this, it's going to be 2.113 equals e to the 5b. That looks like natural log of 2.113 equals 5b. And you're going to divide and find your b value, and your b value equals 0.1496. What this allows us to do is it allows us to write an equation so that we can find when it's been 24 hours. My equation would look like this. Y equals initial time, which again we don't know the very initial, but we can use the 2 hours, 256, times e, the b is 0.1496, and my time, the time that I'm going to put in there is, if I'm using at 2 hours, and then I want to find when is it 24 hours. The time that has elapsed is 22 hours. So I'm going to put 22 in here. That's how much time has passed between the reading that I found at 2 hours and the one I want to find here at 24. So then your final result is 6,880 bacteria. That is it. So your goal is you're going to use the information given. You need to find a B value, your rate, and then rewrite your model here so that you can use it to make other predictions. The radioactive isotope 226Ra has a half-life of 1620 years. This 1620 years is my time it takes for something to be half of. What percent of the present amount will remain after 10,000 years? We need to write a model. Half-life would be decaying, y equals a e to the negative bx. We're starting with the original amount. An original amount would be 100% of, so that's what I'm going to do. So if we have 100% of something, half-life, then you'd have 50% left. E to the negative b, and the time it takes to get that half is 1620. This is my equation I'm going to set up. This is just to find the b value so we can use it later. Divide by 100, you get 0.5 equals e to the negative 1620b. Got to find b. Natural log of 0.5 equals negative 1620b. So as I solve this for b, dividing by the time there, and also include the negative with it, you're going to get a value of 0.00043. That is the amount that I'm going to write my model. I'm going to write my model now, and my model is going to look like this. Y equals initial amount, which is 100%, e to the negative, I'm going to put b in there, 0.00043. Now I include the negative because that's the original model here. This negative is not contained right now in this b value that I found. And then times x. And my x would be, in this case, 10,000 years. So we're going to put 10,000 years in there. And as you calculate that, you're going to be able to tell how much you have left. You can just go ahead and calculate that, and you get y is equal to 1.4%. All right, we've got just a couple more problems left in order to be able to look at each one of these models. And the next problem that we're going to look at is the Gaussian model. The Gaussian model, again, is a normal distribution. It looks like this. It's curved. It's kind of like when you see or hear of tests being put on a normal curve or being curved. Test scores at Nick and Tony's Institute of Technology can be modeled by the following normal distribution, where x represents the test score. Sketch the graph and estimate the average test score. Well, what I would want you to do is put this into y equals, and then you're going to set your domain or your x's. Since they're test scores, we can do from 0 to 100, and then zoom fit. And then in order for us to get the average, your average is the middle. So what is the score here in the middle? Right here, the x value. That's what you're looking for, is an x, which is your score. You can pause the video and calculate the maximum point there, calculate your maximum or that vertex. But you should see that you will get this 82 that I was referring to earlier. So at 82%, that is your mean. All right, we've got our logistic growth. The State Game Commission released 100 animals into a preserve. The agency believes that the carrying capacity of the preserve is 1,200 animals. That's the total. So this is what, if you look at the growth of the preserve, it's going to slowly approach that horizontal asymptote at 1,200. Here's our model, and what we need to predict is how long will it take to reach half of the capacity. Half of the capacity would be 600. So when does 600 equal 1,200 over this model of 1.8 or 1 plus 8 e to the negative 0.1588 t. I would recommend that you pause this video at this point in time and try to solve this on your own algebraically. All right, I'm going to go ahead and copy this over to the other page here, this equation that we're going to solve. So the first thing you're going to want to do is take all of this and multiply it to the other side. 1 plus 8 e to the negative 0.1588t times 600 equals 1200. Your next step would be to divide by 600. 1 plus 8 e to the negative 0.1588t equals 2. And then subtract 1, so 8 e to the negative 0.1588t equals 2 minus the 1 is 1. Now divide by 8, e to the negative 0.1588t equals 0.125, which is 1/8. So to solve this, you're going to do natural log of 0.125 equals negative 0.1588t. So go ahead and calculate that. You're going to get t equals approximately 13 months. All right, we've got one problem left, and that is dealing with the Richter scale and some seismic activity with your earthquakes. On a Richter scale, the magnitude R of an earthquake of intensity I is modeled by the function, where I sub 0 equals 1. So if I sub 0 equals 1, we're just looking at log of I. It's the minimum intensity used for comparison. Intensity is measured by the wave energy, is the measure of the wave energy. So it says in 2001, coast of Peru experienced an earthquake that measured 8.4 on the Richter scale. In 2003, Colima, Mexico experienced a 7.6 on the Richter scale. Find the intensity of each earthquake and compare them. Well, the intensity of Peru would be 8.4 equals log of I. So we can transform that into 10 to the 8.4. Okay? And you'd get a result. Now in Colima, it would be 7.6 equals log of I. So that translates into 10 to the 7.6 power. Each of these would give you their intensities. Now the intensity of the first one is 250,188,643. The intensity of the second earthquake is 39,810,717. In order to find their comparison, you just want to divide these two. So if I divide these two, it's going to be how much larger is the first earthquake in 2001 than the other. And if you divide them, you should get 6.3 times. All right, that is it for the modeling here in this section 3.5. And your assignment is page 225, 19, 21, 27A, and 29 through 41 odd.